Thank you so much for the introduction. I am Marco Pogliano, a PhD student of the Politecnico Torino, working with the E-Lions research group. And today I will present you our work about the 3D printer-based test bench for contactless respiratory monitoring system. I will start my presentation with a question. So why a 3D printer should breathe? We usually use the 3D printer to produce objects in many different applications. So why do we use it to reproduce the breath I've seen in the video? Well, to answer this question, I've prepared a presentation made of 4 points. First of all, I will begin with a small introduction about the radar working principle and the validation method for radar-based system. Then I will show you our proposed test bench, and then I will analyze the breathing simulation results that we have produced. So just a little introduction. We used in our project the frequency modulated continuous wave radar that is composed, of course, of an oscillator that produces the signal that is transmitted by the TX antenna. It is reflected by a target, and then it is received by the RX antenna. The two signals are mixed inside the mixer, low pass filter, and then analyzed. These systems can be used in many different scenarios, from aeronautic to automotive to biomedical engineer. And in fact, if we substitute the target with a human thorax, we can analyze, as in the displacement of the thorax. So in this way, we can extract some medical feature, such as, for example, breathing rate. Radar system can be validated in 3 different ways: by software simulations, test benches, or real scenario tests. We have analyzed 3 features to compare the 3 different methods. Of course, the repeatability is higher in software simulation test benches, while it's lower in a real scenario test, because in particular in biomedical application, for example, the breath breathing, the amplitude and the frequency of the breath change between person to person and also from the same person in different time. So we decided to concentrate our research on produce a test bench that has a high repeatability and high accuracy, and also, of course, a real use feature. And this is our proposed test bench. It is composed of a 3D printer used in a very innovative way. So it is used to reproduce the breath of a person. It is, of course, the radar on a tripod, the fixed, connected via USB to a laptop, where a graphical user interface extracts data and elaborates that. Here I show you the photo of the real application and the video where we can see a plywood panel moving as a breath thorax. We didn't use a simple plywood panel, but we used a dummy. So after a little research, we found a material composed of the ionized water, agar, and gelatin powder that has the same dielectric properties as human skin at 60 GHz. That is the radar working frequency of the radar that we use. And of course, in this way, we have reproduced a real use environment. The center of our work was the G-code generation tool. So the tool that, starting from the signal, will produce the G-code line that will be compiled by the 3D printer. To do this, we have to set by the user the time resolution. Of course, from the signal, we can, for 2 points, have a difference in the amplitude. And from these 2 values, we can calculate the extruder velocity and the new position along the axis. These 2 numbers will be used to produce the G-code line, that is a command part, so move to, the X, Y, Z coordinates where the extruder has to move, and the speed in which he has to move. Of course, moving along the signal, we will have 1 line for each instruction. The compiled lines of the complete lines of G-code will reproduce our movement. This is an example. Probably the yellow wasn't the best color for this presentation, of the simulated signal and what the radar detected movements. As we can see, we have a high correlation between the two signals. For our simulations, we use the sinusoidal movements because they are easier to reproduce. We can fix the frequency, we can fix the amplitude, and of course, they have a high reproducibility due to the periodic signal. And for that reason, we used 2 different type of signals. The first one, signal number 1, as micro movements. So we fix the amplitude along the free burst, varying the frequency of the signal. They are micro movements, so we'd like to analyze just the correlation between the 3D printer movement and what the radar looks at. While signal number 2 is more challenging because we use the frequency and amplitude that are physiological for the briefing. So we had the free burst with a longer duration, 1 minute, and with the same frequency along the signal, but variable amplitude. Here we have the displacement used, so for 10 to 30 millimeters, and these are the frequency, while on the other side we have 12, 7, and 4 millimeters of amplitude and the values of the frequency. The results for signal number 1 are shown in this graph. We can see the amplitude and the brief rate, and we can see that our radar system has an accuracy lower than 1 debrief per minute. That is the medical reference parameter. And also in the table are shown that the percentage error are lower than the 3%. So it's a high accuracy system to test radar system based. Zooming on one of the 3 clusters, we can see that the accuracy is even lower than 1. It's just half of a brief. By signal number 2, that is more challenging, we can see that for the amplitude and brief rate combination, we have the same behavior. So we have a high resolution and a high accuracy. In fact, also in this case, the error is lower than the 3%, with an average error of 0.6 per minute. So in conclusion, we have achieved our goal. So we have created a test bench, we have validated it. It has a high repeatability and high accuracy, and using the dummy and the real brief signals, it's also in a real use environment. Of course, its innovation is that it is based on a general software tool and 3D printers that are well distributed in department, university, but also in different companies. So our goal has been achieved. Last but not least, I would like to acknowledge the A4TSM European project that has supported us, and also the Alliance group from Politecnico di Torino that has supported me personally. And I also want to thank you for the attention.